Okay, good. Clicker works today. Yesterday. Okay. So Brian asked me to talk about exploration and communication. I'm going to have one slide on exploration. And then I'm going to talk about design and how it relates to communication. So let's start with data exploration. So data exploration is something that traditionally in visualization is a thing that we supported heavily. But it's one of these things that we've kind of got a tenuous relationship with for a variety of reasons. But the basic idea behind data exploration is that you want to first acquire your data, right? Simulation or observation or whatever other method you use to acquire your data. You're going to then clean your data. So this could be things like denoising. That's a problem in your field. Or it could be filling in missing data. Many other things that could go with data cleaning. And then you're going to start doing some analysis. Okay? And you're going to do, there are many types of analysis you can do. You can do univariate analysis, multivariate analysis. You can go and do volume rendering to try to identify interesting features in your data. And so one of the places where we run into struggles with doing this is that a lot of times people start looking at their data without knowing what they're looking for, and that's a bad practice. When you start looking at data, you should have in your mind things that you're trying to identify within the data. You should have hypotheses, generally speaking. So it's a good idea to know what you're looking for. Okay? The more precise you are on what you're looking for, the better. You don't have to know exactly what you're looking for. You can discover things as you go, but it's better to know what you're looking for. It's a bad idea to just do a blind search. Oh, I got this new data set. I'm just going to load it up and see what I find. That's a pretty bad idea in general. And this second point particularly relates to the increased criticism of p-hacking, right? This is, I have a whole bunch of variables I collected, and I'm just going to look for something that's statistically significant. Practice you probably shouldn't follow, okay? One solution to that's being increasingly used, I don't know if it's being used in your field, but it's being increasingly used in my field, is doing pre-registrations for your analysis. So basically you come up with a set of analyses ahead of time before you get your data, you run those analyses. And then after that, you can run more analyses, but the pre-registration kind of establishes the fact that you had some ideas before what you were actually doing. Okay, so that's the general data exploration process. You use all the tools you're familiar with. There are no special tools involved in it. It's more of a thought process than it is a particular set of tools for being effective in this case. Yes.
Why is it a bad idea to do a blind search within data? Because I would think that if you do a blind search, that would be a really good way to eliminate any biases that you might not be aware of in your analysis.
So it really depends. The context I'm really saying this is within the context of things that are your equivalent of p-hacking. So if you have a data set and you just load it up to see if there's something interesting in there, that's usually a bad way to make a scientific discovery, unless it's followed up by experiments that actually validate a hypothesis, right? So you can do an exploration, find things to eliminate things, but it should not be the end of the analysis. That should be the beginning of a hypothesis that you then have.
I see. Thank you.
There was another one. Did I answer it or did it go away?
I had
a similar question.
Yeah.
Okay, so now let's talk a little bit about design. So when I talk about design, what I'm talking about is choosing the type of visualization that you're going to use for your analysis. So it turns out that you shouldn't just pick the thing that you're used to using all the time, and you shouldn't just randomly pick what visualization you choose. It turns out there's a process for selecting these things. And it's a process that I'm not going to give you specifics of how to of the choices that you make, but I'm going to give you another process for you to make the decisions that you're doing. So this is a model for designing visualizations by a visualization researcher named Tamara Munzner. And basically it breaks down into 4 different levels of abstraction. And the idea behind these 4 different levels is that you want to think about each of these situations before you move on to the next one. And you want to validate that what you're doing within each level of this hierarchy is good before you, and if it's not, you want to move back to rethinking what's going on. Okay, so let me go through these. Okay, so the first one of these is the domain situation. So this is really figuring out what you're trying to target and what the domain of your problem actually happens to be. For most of you, this is going to be predefined what the domain target is. So for most of you, it's predefined because you have a scientific field already, and so that's great. You're not going to have much to worry about here. But where you will come into this model is in the data and task abstraction. And so this is the idea that you have a data set, you have something you want to discover about that data set, and you need to make sure you're very specific about what those things are, because the specificity of those things is going to define what type of visualization you use. Do you need to use a scatter plot, or do you need to use a histogram? These are driven by what data you have and what task you're trying to perform, or what analysis you're trying to perform on the data. Once you've decided what the data is, or once you have your data and you've decided what task you're trying to perform, then you can start to finally think about the visual encoding, which is basically a fancy way of saying, what visualization are you going to use to look at your data? Are you going to use a scatter plot? Are you going to use a histogram? Are you going to use volume rendering? Okay. Excuse me. The last one is technique and algorithm. This one, again, probably won't apply to most of what you do. This is much more for people in my field who are designing unique visualizations. For you, you're probably not designing unique visualizations, so you're going to really focus on these two. What analysis I'm trying to do and what visualization supports that particular analysis. Okay. So as you do if we do our activity today, you should kind of be thinking about that. Like, what am I trying to show, and what visualization am I going to use to show that thing that I'm trying to show? Okay, so there are a lot of design principles out there, and these design principles have a lot to do with how we communicate our data. So Edward Tufte is one of the early leaders in design in the field of visualization. He's also someone who a lot of people have take issue with some of his design principles. So, when early people tend to also get a little controversial with some of their ideas. So I'll try to present some of his ideas that are, some of them are, most of them people agree with, but some of them are a little bit more on the controversial side, and I'll mention those as we go. But basically, we're going to focus on two things, which are graphical integrity, so making sure that your graphics are accurate, and design principles that make your graphics easier to read. And these are really important for communication. So graphical integrity is the idea of clear, detailed, thorough labeling so that you can defeat any distortion or ambiguity. It goes well beyond this, but that's his main point is that the labeling is. This is a really nice quote from him that kind of captures his design idea. So you want to design a visualization or pick a visualization that's going to have the greatest number of ideas. It's going to show you the most stuff in the shortest amount of time, so it's going to be really easy to understand what's going on with the least amount of ink, so not having too much on the screen, and you want to keep the graphic as small as possible. Many of these are counter to one another. These principles are counter to one another, but it's a good way to think about how to optimize the visualization. And this is the Einstein quote that related to this, right? An explanation should be as simple as possible, but no simpler. Same idea with your visualization. It should be as simple as possible, but no simpler. Okay. So one aspect of this that's important is making sure that when you pick a visualization, you're picking the one that is most effective. So this chart up here lists the common encoding channels. I showed this to you yesterday when we did the activity. You may have seen this before in someone else's slides. But these are some of the different ways that we can encode data. We can encode data with position, top two. We can encode things with size, like the length of the area. We can use angles, and we can use color. The interesting thing about this chart is that it's also set up in a way to be a proxy for how effective these different things are. So the things that are on top are the things that are most effective, and the things that are on the bottom are least effective. So what this is saying is that things that use position are going to be more effective than things that use color. In general, there are specific cases where that is. Okay. On the left here, we have things that are quantitative in nature, and these are categorical. Okay. Let's look at some of these in practice. So here we have two bar charts. Okay, one is your standard bar chart that's on a common baseline. Another one has the bars offset from it. visualization like this very often, but where you do run into this is with stacked bar charts, right? You might have a stack that's underneath of here, and you want to compare all the green bars. Okay, so this is not a totally contrived example. Okay, so if you're looking at these and you're trying to compare them, what you're going to do is you're going to do this thing that's positioned on a common scale. That is, they all have the same baseline, and you're basically going to look at the tops of them and compare the tops of them. It's a very easy comparison. Whereas when you go over here, it's not a hard comparison because they are actually somewhat aligned, but the comparison is a lot harder because you're using length instead of having a common baseline. And as they get closer in size and offset more, it becomes more and more difficult to interpret them. Whereas these, even if they're very, very close, you're gonna be able to detect a few pixels of difference. One example. Here's another example. Here we have two different encoding channels. Here we're on the top, we're using the area. So whatever variable this is being represented by how large the circles are, the total pixels in the circles. And on the bottom, we're using color. Okay. So in this chart, if I ask you which one's larger, Illinois or Georgia, this is pretty hard, right? They're both pretty washed out, pretty difficult. Here, it's a little bit easier. It's not easy by any means, right? These are not particularly strong channels. It's kind of in the middle of the pack, but it's definitely easier than this is. Right? You could, if I asked you relative to Texas, how large is Illinois? That's not that hard of a task up here. Here it's a lot harder of a task. So what this is calling for is picking visualizations that use these things that are on the top. And if you think about the types of visualizations we commonly use, things like scatter plots, that's positioned on a common scale, right? It's, you have a baseline, two axes that are baseline, position. Same thing with a bar chart, that uses this. So those are going to be more effective types of visualization than some of these other ones. Here's another example. This is a gene encoding on the left, and these are line charts that are equivalent of some of those gene encodings. Right? So if you look at one of these series of colors, and then you compare it to one of these series of line charts over here, the series of colors is hard to interpret. Right? The line chart's pretty easy to interpret and compare. Right? Like what are these two green bars next to each other? Whereas you can compare these two line charts much more easily. And that's because this is using color and this is using position on a common scale. Much easier to interpret. Granted, it takes up more space, right? This is many, many genes that are encoded here, and this is still a lot, but it's a way smaller number than in those pictures over there. But it makes it much easier to interpret. 3D is another place where things can be particularly challenging. So as was kind of pointed out this morning, a lot of the 3D pictures that you use are good for exploration to see if things are there. They're good for making pictures if you're gonna do some outreach. But doing analysis in 3D is a little bit iffy sometimes. So this is just one example of where analysis in 3D was actually shown to be much more difficult analysis. So these are visualizations of the flow of blood through arteries. And what they did was they compared the 3D version of this to a version where they basically cut the artery and laid it out flat. And what they showed is that people were significantly more accurate in their judgments when they were doing the 2D version that was cut up and flattened out versus the 3D version. Okay, so you could use this to get intuitions, but you should use something else to actually verify what you're seeing. I think it's kind of the same point that was made this morning. Okay, so this is the communications, the right's the communications thing, the left thing is the actual analysis thing. Okay, so scales on charts are a really common place where things are problematic. Okay, so I'm going to give you some examples of places where scales have been messed with to send a certain message. So this is the only climate change chart you'll ever need to see. Does anyone know what's wrong with this? Scale's a mess, right? It goes from 0 degrees to 110 degrees. If our average global temperature is anywhere near either of those, we're all icebergs or we're cooked, right? So this is not realistic to to the challenge that we're facing, right? There's a much smaller region that is that's important. Okay. People are always concerned about federal debt. Doesn't look like a problem to me. Well, they just messed with the scale to make it look like a smaller problem than it really is. Mass shooting, something they're always in the news. Very sad, right? Doesn't look like it's a problem here.
Why does it go negative?
Artifact, it actually doesn't go negative, but artifact of the drawing that it looks like. These are actually tick marks. That it looks like.
The y-axis goes negative.
Oh, what? Yeah, that's good. What? I don't know what a negative shooting is. That's a group hug or something. Okay. World population. From the beginning of time till now, basically zero. Anyone seen this one before?
Yes.
Okay, if you've seen it, don't answer. What's wrong with this chart? So this is since Florida enacted the stand your ground law, this is the number of gun deaths in Florida. What's wrong with that? What does it look like? It's upside down. Scale is upside down. Okay, so we expect scales to start at 0 and go to 1,000. This starts at 0 up here and goes down to 1,000. So what it does is it makes you think the trend is the opposite of what it is. Technically accurate, it's well labeled, but it breaks convention. And so your first intuition is that, oh, you know what? Stand your ground worked. Fewer people get shot. And the truth is, stand your ground did not work. More people are getting shot. I don't know if that, I honestly don't know if that was his intention to get more people shot or not. Scales and baselines are this place where we have a lot of trouble with communicating things that we have to be very, very careful. So this is a picture. It's a very old picture that was in one of Tufte's books. And it talks about coal mining. It's a picture from coal mining industry in the 70s. Okay, it's 70, 71, 72, 73, 74. Okay, it's got three different variables. Got the operating revenue on the left, net loss, net income on the middle, and then R&D on the right. Okay. And it's got these values. You can see what the values are. But what's a problem with this? What do you think is weird about it?
Scales are so.
Scales are weird, right? So what's the baseline? So let's just take net income as an example. If you're going to measure these things relative to one another, the baseline is really big negative number. So that implies that if somebody were down here, basically the whole industry would be dead. The baseline's a mess. And so it makes this, it sort of squishes these values a little bit, right? It makes it not seem as dramatic as they maybe are. Okay. Let's say this is the stock market from 1998 through 2002. What do you think is happening in the stock market right now? Like bad news? Yeah, a little bit like bad news, right? Did the stock market crash? Oh, it looks kind of like a crash to me. But maybe it didn't crash, right? So this had a scale that was 450 to 500. The range of the data seems like a completely reasonable scale, but it doesn't give you the full perspective. Start at 0. That just looks like a down day, not like a stock market crash. Okay. So what we lost with the other visualization was the content. Yes.
This kind of seems to contradict a little bit of what we learned yesterday. I remember yesterday you showed a plot and then you showed a second plot where it was like just zoomed in on the data. And I had been taught that using broken axes like that could be misleading. And that's kind of what you're telling us now. So how do those things like?
So it turns out it's completely situational. I have some recommendations as we go through, but it is entirely situational. Basically, what it boils down to is if the standard practice is to show things that are just within a particular data range, then you want to do that. If it turns out that it's something that that has a long-term trend or you want to keep good context, you generally want to start with 0 and go up to the value. But those are just general guidelines. It's very situational beyond that.
Yeah, and I'll note, previous session when we were discussing this, the other thing you can do is, I think it's called parts in a whole. So you can show this version. You now have a lot of white space. You could do a small blow up that gives you your data range.
People will sometimes call these mini maps. So they'll show the full data as a little mini map right here, and then in that mini map they'll show a little square that gives you this. And that's a context-based method that's very useful as well.
So, but for the stock market example, what people look at is like, since it's continually growing, they look at like if we to like this previous baseline. So this particular example, which might be a little strange, but like we wouldn't look at 0, but we would rather look at like what was the baseline 10 years ago. And
Well, so actually, if you bring up like a stock on Google, it'll start at 0. But and that's in part because stocks are always growing in this sort of unsustainable exponential way. And so you always have like good context for the recent history and bad context for the distant past, because the distant past gets really shrunk, and then recent history got most of the scale. But that's a very specific case. There was just a paper by I think some Swedish guy that said the stock market's going to explode in 2050 because it's growing exponentially. Look that up. So now if you look with more context, right, this is more of what the stock market does. Maybe the stock market is a little more exponential than this. It's more linear. The stock market's, 40, 50 years ago has smaller value than it does today. And you have this nice context of it going. Right? With the stock market, we're concerned about like the percentage that it goes down, not the absolute value that it goes down. So this kind of chart gives us that perspective of the percentage. And then this is the little piece of it that we're. Okay, so when should you use 0 baseline? Again, it really depends. There are a lot of context-based things, but here's one way to think about it. If you want to compare overall proportions, then you want to use a 0 baseline. Okay, so these are some people. Say, let's see, it's heights. Okay, so if you want to compare their overall height of the people, having a 0 baseline makes sense. Gives you a fair comparison of their overall height. If you want to just compare their relative positions, so you want to know who's taller than whom, it's going to be easier to do that if you start with a different baseline, because you're going to have basically more of the chart dedicated to showing the differences. Right? That's really what's happening is you're dedicating more of the chart to differences, and here you're dedicating more of the chart to the overall trade-off that you make.
Would you say that using a bar chart like that is bad when it isn't 0 baseline? Because people look at the length.
It could be, yeah. Yeah, context dependent, but yeah, generally say probably bad.
Is it a good idea to use a bar chart at all? Because I know like Tufty
So
argues against them.
yeah, I actually think bar charts are the most useful chart. I find myself using bar charts like all the time, like 90% of charts. Like that should just be a bar chart instead of whatever. So you have to think a little bit about what bar charts are conveying. They're conveying like a collection of things, right? So like a collection of marbles, right? You're putting all the marbles into your jar and you're seeing how many marbles you have. So histograms are a great example of where bar charts make natural sense. You're just taking all your marbles, being whatever phenomenon you're counting, and putting them. So they're quite useful for that. But there are also places where they shouldn't be used as time series. Probably not a bar chart, right? You want to use some sort of connection trend. Most of these things are very there aren't steadfast rules for it, which makes them extra hard. You can also think about truncating the y-axis or using a non-zero baseline if 0 doesn't make sense. So just in the context of what you're talking about, 0 doesn't make sense. If you want to emphasize relative positions of things, or if it's just the normal thing to do. So in a stock chart, if the normal thing is to not show 0 as a baseline, then you don't show 0 as a baseline. If people are used to that practice. What you don't want to do is you don't want to break the norm whenever possible. That's what that stand your ground visualization did. It broke the norm, and so it made it difficult to interpret. Right, so here's a case where maybe it makes sense to not have a zero baseline, right? US GDP doesn't look that interesting if you look at it just from a zero baseline, whereas look at it from a baseline of 14 trillion, it looks more interesting. You can actually see some movement in the whole chart. Okay. So next up is dealing with outliers in the visualization. Okay, so we have a chart and we have some outliers in our data. Okay, so what are some options? So we have one option here, cut them out, right? Just ignore them. You can create a chart where you identify the outliers, right? So you cut them out, and then you say some special mark at the end of the chart says, hey, there's an outlier over there. What else? What are you all going to do if you have outliers in your data?
Use a log norm scale.
Okay, so you could use a log scale. Good option. And then we had another one earlier, which was broken in scales. Okay, okay, so flip them out is one option. Right here, we flipped them out. In this case, we didn't mark them. Ideally, you'd say, hey, there's one outlier here and one outlier wherever it was. Maybe it's okay. But you've lost some data, right? If those data happen to be noise, that's probably okay. But if the data aren't noise, then incomplete data that you're presenting on the screen, right? And this is the situation. This is population of countries. Those were not true. Those weren't errors. Those weren't noise. These are just two really big countries, right? This is South Asia. It's probably India, and that's probably China, right? So we just cut India and China out of the mix. That's probably not a good way to represent your data. Okay. Break the scales is another option. So breaking the scales basically says we're going to have multiple scales in our chart, and we're going to have some clear break between. You have to be very careful if you're going to do this. Some places it's okay to use them. Most places it's not. This is an example of a really bad broken scale, because while the scale is broken, this line is a horrible idea because it doesn't represent the real gradient of this thing, right? In fact, it's much shallower of a gradient than is represented in that line. Over here, this is a little bit better because it's got a very clear break in the scales, but still there's a risk of misinterpretation of what's going on here, right? It looks like it's going down in a linear way when it's not. It's not for these outliers. Okay, so breaking scales is an option. Again, you should really only use this if it's the practice, not as a thing that you're going to do. Then we can do log scales. Okay, so log scales are another great way to do these sort of things. So here you see a log scale of this data, and it's basically compressing those really large numbers. The challenge with log scales is, again, it depends if your field is used to using log scales, but there can be misinterpretation of what the log scale really means as far as, hey, this trend looks linear, but it's not a trend in the log scale, not a linear trend in the log scale. Okay, so you have to be careful. Yes.
I just want to add that outside of your field, never assume that someone uses log scales. Like a public talk,
Yeah, or general public does not know what a log scale is.
not assume the log scale.
Even somebody who's scientifically trained, don't assume that they understand a log scale, because there are some sciences that use them regularly and others that don't.
And it looks for the original graph left, they also changed the scale in the other half.
I think that's actually a misperception. I don't think they did. I think it looks like it's log scale, but it's not.
Not log scale, just in each tick is 50 laptop. Each tick.
Yeah. So this is a broken scale, right? This is each tick being 50 here, and this is each tick being 400 here. Okay. So this is linear with a broken scale. This over here is same data. Okay. So you can see they kind of have similar effects to them, right? Like this thing, these points and these points are kind of in similar spots, but the interpretation is slightly different because here you have the broken scale, and here you have the log scale. Okay, so log scales in this case look a whole lot better, right? This was the linear scale, this is the log scale. Okay, but again, it makes interpretation a little bit more difficult because you have to realize that these things are going up in an order of magnitude. In this case, it's a base 10 log scale. And so you have to realize that, you know, these things are 10 times this, right? As opposed to being 1 time. So interpretation, misinterpretations abound if you're choosing log scales. Be very careful.
Just out of curiosity, what's the largest country in the American continent? Is that the USA or is that?
Probably US. Probably US, Mexico, and then Canada, I would guess. I would I'd say this is probably US, it's probably Mexico. Okay, so thing to keep in mind is that log scales are really representing something different than a linear scale. A linear scale is really representing the data directly. A log scale is really representing more of something like percentage or change. So it's a very different type of interpretation. And again, to say the practice, go for it. If it's not, be very, 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 very careful. Okay. Aspect ratio charts. Okay. Turns out all these things make a difference. You want to communicate something to people. These 3 things are the same chart. They all look really, really different, don't they? Amazing what a difference aspect ratio can make, right? This thing makes it look like things are going up like crazy. This thing, like things are pretty flat. This thing is just right. It's like so you have to be careful when you're choosing the aspect ratio of your chart. You don't just fit it into whatever space you got, because that can actually change how people interpret it. Okay, so there are rules of thumb, but there's no steadfast rule. An aspect ratio of about 3 to 1 is a good rule of thumb. But there are other rules of thumb that come from other places that talk about how to optimize the perception of different features and things. That's probably a bit much for what you need, but generally you should try to target an aspect ratio about 3. So here's a situation where interpretation is quite different based upon the aspect ratio of your chart. So again, these are the same chart. This one is much taller, wide. This one's wider and not as tall. So let me just ask you, what do you note about the thing on the left? What jumps out at you? Like super spiky, right? Like a lot of dips, a lot of spikes. Okay. You know, what do you see more of?
The width.
With looks more like cyclical, right? It's like more of a pattern. So you're seeing very different patterns based upon the aspect ratio. Exactly the same data though.
Looks like both the charts have a little bit of offset between the bottom line and the 0. And that offset is a much bigger fraction of the total variance on the right than on the left.
I don't think it is, because I think they just have the same amount of buffer between 0 and the bottom of the chart.
Yeah.
So in that sense, it is more, but
The right side one doesn't look like it approaches 0 nearly as much as the left one.
right,
Looks
yeah,
like it approaches 0.
yeah, that is some effect because of this extra space that they put on. So it gives you a different perspective. All these things are very minute, but they give you very different perspectives.
Something interesting that I'm noticing while looking at this is, like, to me, like the left side, like as an observational astronomer, looks like noise, and the right side looks like something that maybe would be like an emission line. And I think it's really interesting because the way that I have been trained to interpret data changes how I specifically would interpret this data. So I feel like it's really important to like think about the context that your audience has.
Absolutely.
And yeah.
That's right. If you're talking to somebody who's in the same field, they're going to approach it the same way you do and think, oh, that's noise. But people, maybe general population people, are going to think that's actually signal. Right? They're going to see big spikes and be like, oh, that's an important thing. But it's also interesting that you're saying, oh, this looks like noise, and this starts to look like a signal. That should worry the heck out of you that 2 different pictures of exactly the same data are doing that to your brain.
Because we were talking about these offset on 0, what are your thoughts on like placing zero, peak of zero with an offset or not doing that? Is there any reasoning?
I would have had zero right at the baseline. I wouldn't have had it offset at all.
Is there any, okay,
It's a personal preference, honestly. I think this is more confusing to have it offset like that. Less confusing to have it lined up perfectly, but the designer of this chart decided they wanted like a little boundary around the data. And so that's fine. So one rule of thumb is 3:1 aspect ratio. Another rule of thumb is to try to make these things angle to about 45 degrees. So there's some research that says that our ability to detect angle is kind of optimal, actually at about 60 degrees. We're most accurate with detecting the angle of these different features in the charts. Okay. So it turns out that when we're interpreting line charts like this, we kind of look for peaks, for spikes, and then we look at angles. And so optimizing the angle is just one approach. So here's an example. Whether this is better than that is very situational, but that's kind of what it looks like. That's more of that's an aspect ratio of 7.7, and this is about 1.17, where the orientation is about 49. Which one's better? So there's a measurement that Tufte introduced that's another good rule of thumb thing. It's not something that you would regularly calculate, but it's something to think about when you're making a graphic. And this is what's known as the lie factor. And the idea behind the lie factor is that you're showing some effect in the chart, and there's some matching effect in the data. And you want to measure the ratio of the effect in the chart to the effect in the data. Basically, you want to say the effect that I see in the chart should be equivalent to the effect in the data, right? If it's 10 in the chart, it should look like 10 in the data. Here's an example where it's broken. This is more of an infographic, but what we have is we have years on the left, and we have fuel efficiency standards on the right. And what they're doing is they're trying to use this little road to show the increase in the fuel efficiency standard. Okay, so you have at the very back in 1978, you have a line that is 0.6 inches long and measures 18. And all the way in 1985, you have a line that measures 5.3 inches long and 27.5 gallons. It looks like from the chart, it looks like we've done really, really well, right? But if you actually calculate the lie factor here, that is, you calculate the effect size of the data, which is going from 18 to 27. Okay, so that's what? 50%, less than 50% increase relative to a line that was 0.6 inches is now 5.3 inches, going up about 9 times. You can come up with a lie factor, which ends up to this number, 5.8. So what this is saying is that this chart is exaggerating the effect of the fuel standard change by 5.8 times. So it's giving the impression that the fuel efficiency standards have gone up way more than they have. Okay, so this falls into this category of lying with charts. Okay, this is a more accurate chart. Okay, this is a line chart of this, and you can see this has a lie factor of 1. That is the data values relative to the chart values are. You can find this sort of thing in the real world. I found this chart in Wired many years ago, and it didn't have a scale. And so I didn't know whether this thing was measuring with height or measuring with pixels. And so I actually went and used this lie factor calculation to figure out the fact that if this is measuring with height, there's actually lie in all of these. If it's measuring these different variables with area, then there's no lie. So I was able to sort of back compute with this lie factor how they were actually encoding the data. They were encoding it by area, but they could have been encoding it by some other size. It's easier to specify the radius of a circle than to specify the area of a circle when you're drawing a circle. There's a lot more math involved. And as we discussed, a bunch of computer scientists don't like math. Okay, so showing variation in data, not in design. Okay, what's wrong with this chart? This is world population 2008 by country. What's very dramatic about this? China and India, right? They look quite large. Are they, what's wrong about how large they are, right? They do have really large populations relative to the rest of the world.
Their width is being increased as well, is that right?
Yeah, so their area is going up, and area goes up, you know, in a squared manner, as opposed to the number of people, which is going up in a linear manner, right? So it's making China and India look much larger than they actually. They're still pretty large, but that's overly dramatic, right? This is a more accurate way, a bar chart. Okay, we're counting people, counting marbles. Still very big countries, but the lie of this, right? Your perception of how many people are in India or China, and that is going to be much larger than relative perception of how many people are in India and China relative to the US is much larger there. Okay. So some rules of thumb for designing good charts is one is what's known as data to ink ratio. So this is the idea of how much you're drawing on the screen relative to how much of what you're drawing on the screen is actually used for data. So this is a 3D bar chart, which gives me the heebie-jeebies to look at. And the reason it gives me the heebie-jeebies, there are several reasons for it. One is that it uses a whole bunch of ink that is unrelated to the data, right? The part of this that's related to the data is this and here, right? The rest of it is just fanciness. The other thing is the fact that it's sort of angled makes it really hard to interpret. Okay, so this has a really high data ink ratio, or really low data ink ratio, right? That is, uses very little data for the data and a lot of ink for the graphic itself. A regular bar chart would be much better, much easier to interpret. It doesn't look as cool, right? This looks pretty nice. This looks fine, but it's not quite as informative. So a place where this can play a role for you all. You guys draw these a lot, right? You know what box plots are. Do you have a question for him?
Yeah, like what are we looking at? What's like the 0 to 24,000?
So this is the measurement of triglycerides, which is one of your medical measurements for your cholesterol. And this is by income group, or is income group, and then this is males and females.
And so why is it repeated? Like it seems like the green and the red.
So this is males who make less than $25,000, and this is females who make less than $25,000.
That's right, but like green and red have the same.
Ooh, that's a typo. Yeah, that's a typo. I don't know why that's like that. You know, I've shown the slide many times and nobody's pointed it out. Yeah, I have a different slide of this where that's not messed up, but this one is clearly messed up. I have to go look at what it is. All those things. Okay, so box plots. Some of you use these regularly. Yes, no, maybe, no, really.
I don't like
You don't like them, but you know what they are.
really.
Yeah. That's why you don't like them. So you have a lot of data points, and you want to represent their distribution. A box plot is a good way to represent the distribution. What it generally does, it represents the mean. It represents the second and third quartiles, and then it represents the mins and the maxes. So you can kind of get a sense of the distribution. If there are other variations on the box plots where people like use these as standard deviations, there are versions where people have higher order statistics. I'll show some that have higher order statistics. So
Question.
yeah.
So that means that the mean would be the actual like totality.
Yeah, the measure. So this data to ink ratio thing would basically say, oh, this is good, but if you use less ink, you're going to do better. So this is showing you the same thing. And it's got a dot where the mean is. It's got your quartiles here, and it's got your mins and your maxes there. But it turns out that those things aren't that easy to read. It turns out what happens in your brain is that you're reconstructing a whole bunch of stuff. And so it makes it actually harder to read. Turns out that the easiest thing to use is to just use a regular box plot for representing. While I say minimize how much ink you're using, that's not always true. Ink can help people to interpret the data a little bit better. They tested a bunch of different types of these things, and they found that this one, the standard one, is consistent.
I will maybe offer a counterpoint to counterpoint. Because if you go one slide back.
This one?
So I think I would read the means better from the right one than from the left one, because they're not round in horizontal line.
Yeah, so if you're looking at the specific mean, I agree with you. If you're trying to reconstruct the entire distribution, I would argue that this thing's harder.
Yeah.
So
Yeah,
it's very context dependent.
So it depends what you want to read.
Depends what you want to reconstruct as. So. Okay. So generally speaking, reducing the ink is good, but not too much, which is also not a very helpful rule of thumb, right? Okay, so one spot where Tufte kind of shined and people kind of push back on him is this idea of chart junk. So chart junk is simply stuff that's been added to a chart to make it more interesting. Okay, these are two examples that have chart junk. So these are very interesting pictures, right? And they have data in them. They're both. This is a line chart on the left and an area chart on the right. They're relatively true to their actual data. So it's not like they're lying. And this one, you can even see the grid that they used. The grid. So they're pretty genuine to their data, but they're also have all this stuff on them that is potentially distracting. Okay. Here's the real bar chart of this thing that you see over here on the left. And like if you look at it, like they're actually pretty accurate. You read it relatively reasonably. So it hasn't gone crazy. So what Tufte argues is you should never use chart junk, or if you're going to use chart junk, it shouldn't interfere with your chart at all. Okay, here's your line chart for the thing on the left again, pretty similar. So Tufte says avoid chart junk. Chart junk can include things like extra stuff that you draw on the chart that's intended to help people read the chart, but really is just distracting. So for example, these grid lines, they're just distracting too much. So you want to remove grid. The background that we have here, it's not really adding anything to the mix, just making it bluer. So get rid of stuff like the background. These extra tick marks on the sides and on the box on the top. It's not really adding anything to it. Okay. Tufte would even argue that the tick marks over here are unnecessary. I disagree. I think this is better than this one, but this is a personalized thing. So this is the version that Tufte would argue for. I would argue for this version. Okay. So the counterpoint to this whole remove the chart junk thing is something that I mentioned yesterday, which is the memorability of a chart. So it turns out that there's been some research looking at what people remember when they see a visualization. And they remember this stuff, the unique stuff. They don't remember your standard boring bar chart. So if you're trying to make a point, doing something that's more unique will create a memorable experience for you. Whereas doing something that's more like this is a little bit easier to read, a little bit more accurate of a visualization. So you have to kind of balance things. So when you're doing outreach, this kind of stuff, I know it's tough. This kind of stuff sells. But if you're writing a paper, probably more of this. I don't think anyone's going to accept the paper that's got this. Unless you're in the visualization community and you're writing about chart. Okay, data density. So this is about how much data you're shoving onto the screen. You guys have a lot of data, right? So you want to shove all that onto your picture, right? Don't do that. Okay, it's a bad idea. So you want to. What Tufte claims is you should maximize the data density. That is, you should get the most data on the screen relative to the number of graphics. So this is a Tufteism. Sorry for that text overlap. This is a whole bunch of data on the screen. How much of that are you actually attending to? Very small amount. Right? So, well, it seems like a good idea to just throw everything on the screen. The more you throw on the screen, the less you're actually going to attend to. And that means that you're going to miss things in your data. You want to be smarter about what you put on the screen so that you actually attend to it. These are those gene things that I showed earlier. The little gene profiles. These are just line charts of the gene profiles as opposed to being the color version.
So could you use something like color coding for the area of the actual bars? to encode kind of a second layer of information.
You could encode more information via something like color as well.
Then you read as an image that you can then zoom into.
Yep.
And have like a layer.
Yep, you could do that if you want. That's what your goal is for the data.
Get into this, but I mean, it's one thing that I think of that, like, so many of our papers nowadays have, that is a lot at once, is a corner plot from our MCMC runs. And man, definitely do we just like often skim past those and assume they're showing it as proof that their MCMC is good, and don't like look into it. And if we want to use it, because that's a lot of space, that's usually takes up a whole page of a paper. You or anyone else in this room have like a thought on reducing that?
I haven't seen those before. Do you have a thought on that?
Yeah, I haven't, so a generic thought that I'll provide for everyone is that when you need to provide a lot of detail, but you're worried that it's going to be distracting, that's literally what appendices are for. I think everyone underuses the option to do an appendix. If you have a crazy hard calculation that requires 100 lines, how about this is the result, the appendix? Because lots of people reading the paper won't want to do 100 lines to get to your final result. Same thing for very large corner plot. Often, a lot of those are parameters that you're marginalizing over. And there's probably only 2 or 3 things you care about. 2 or 3 things go in the actual figure in the paper, and then you say that all of the marginalized parameters, you can see that in the appendix. These are great. They are correct. They make your paper more readable. Sorry.
Absolutely, great. Yeah. Until your reviewer says, why didn't you put that in the paper? Because they didn't look at the appendix. Right? Even though you said see appendix. Okay. So Tufte also pushes for shrinking graphics. So you want to kind of shrink things as small as they could possibly be. All of us who've written a paper do this, right? We make them as small as possible so we can cram as much junk into our paper as possible. So I don't think I need to tell you on this particular idea. But you want to make sure that they're small enough to still be interpretable, but as small as possible. Something that's kind of a cool technique that you'll sometimes see if you go to web pages that talk about things like stocks or businesses are the idea of spark lines, which are simply charts that are generally line charts that are in line with the text. So this is a technique that you can use well in your papers to go ahead and impress your reviewers or make them mad. Another thing that people love to do with visualizations is they love to cram too much on them when in fact it might be better to separate the data. So here we have a bunch of data that are different classes, different types. And what we've done on this thing on the right is we use different shapes. And it's really hard to see any patterns in this thing on the right. Whereas if you break them out into what we would call small multiples, you can see the patterns within each individual data types. You can see there's a cluster here, or 2 clusters here. You can see the patterns much better when you've broken them out than when you have them all together. At the same time, there are certain patterns, not in this particular chart, but certain patterns that would be more visible with the group instead of the small multiples. So you really need to look kind of at both simultaneously. Okay. Another thing that's really common, and maybe you do this inadvertently, but it has a name, which is called trellis plotting, which is something that you do when you have multiple variables. What you do is you organize the variables in such a way that you show multiple charts of the variables in an organized pattern. So here we have several different variables associated with different locations. And so what we've done is we showed several different charts that can be configured in many different orientations, so that you can compare the different locations. In this case, this is different cities, and you can compare the values across cities by having many of these small multiple plots side by side. Okay, so the only challenge with these types of things is that it turns out that our vision is pretty limited. I've mentioned this before. It's kind of a theme for me. There's a small but significant amount of research into how limited our vision is and how little we actually see when we look at charts. So there are several ways in which we're limited. One is the illusion of visual bandwidth. So individuals will overpredict what they will see in a chart, what relative to what they'll actually become aware of. And so you see all this data, you make a chart that's got like all your data in it, you're like, oh, I'm gonna look at this thing and I'm gonna see everything. No, you've over predicted what you're gonna see. Okay. There's overestimation of breadth. So being able to take in the entire scene at once is something that a lot of people think you're able to do. Again, I just need a bigger screen and I'm gonna be able to take everything in. It's not the way our eyes work, right? Our eyes are very focused in what they do. And our brain kind of fills in a lot of this. And this relates to the overestimation of continents, which is believing that you're going to attend or look at a higher proportion of things that you're actually going. You're going to focus in on certain parts of the display where you see a feature that draws your attention, right? There's a cluster of things right there. My eyes are going to go to that. I'm not going to attend to the rest of the display. There's not uniform attention across the display. And overestimation of depth, which means that you're going to look at things and you're going to understand them really well. So you're going to stare at something and you're going to understand it. So all of these are different forms of limitation of our visual perception with respect to looking at charts. Okay. So now let me give a few slides on that are going to lead into our activity. Okay, and this is on misleading. So this is a very misleading visualization. It turns out that's Steve Jobs introducing the iPhone. And this is a common thing that you'll see, particularly in marketing, but I'll show you some other examples in politics as well. Okay. The idea is that you show a chart that's true, well, that's accurate, but it is a chart that is deceptive to a person. So this is that chart. And the part of it that's deceptive is that you put Apple down here at the bottom, and this is a 3D pie chart. And so what it does is it gives you this perception of the size that Apple occupies, because Apple is both closer and you can see this bottom that's associated with Apple. So it gives you, so the chart data is accurate, but the perception it gives you is wrong. This is more realistic, and I would say a bar chart's even better, how well Apple is doing. Right? Here, this 39% looks a lot smaller. It looks almost similarly sized to the 20% of Apple. Here, okay. Another place where people can get tricked is in what are known as dual axis charts. So this is where you have two different variables that you want to show in a common chart. On the left, you have global GDP, and here you have the GDP per Germany. Okay. It looks like they're going together, right? Could be confusing because somebody could say, "Oh, these are equal," but it gets even worse because it turns out that you can mess with the scales of each of these, and you can make all sorts of different interpretations, right? There, Germany's flat and the globe is going up. Here, Germany's going up and the global is flat. So you can see a lot of different interpretations that can come out of these just by messing a little bit with the scales. So it's that scale problem exaggerated, okay? You're better off making these separate, but even if you make them separate, you can still trick people, right? You can still mess with the scales and make it so that you can see a trend in one and no trend in another. Turns out politicians love to do this sort of stuff, but they're even worse about it than this is. Like this is real data. Politicians just make stuff up. Okay, so this is a Planned Parenthood chart. Turns out this is a dual axis chart. You can see cancer screenings and prevention services going down pretty extremely, and abortions going up pretty extremely. This is back in 2013. Turns out this is what the chart really looks like if you have them on a common scale. So abortions made a little tick upwards, and screenings did come down, but it's still significantly more than the abortions. Whereas you look at that chart, and it looks like they're doing way more abortions than they are doing cancer screening. Okay. This is it doesn't matter which political party you look at. They both do this. So that was from a Republican congressman. This is from the Obama White House. This is about how much better students are doing. This is 75% down here. It's got 5 books, and then this is 82% that has about 3 times many books.
How many it takes to finish the study?
Ron DeSantis' Florida at 0 books now, right? Oh, God. Okay. So this is maybe a little bit more accurate, gives you more perspective on what's going on. You go all the way back to Reagan, Bush times, and to Obama, and you can see that there is a climb, but it's not nearly as extreme as the chart on the left would indicate to you. This is a famous one, okay? This one is, this is true to the data, although there's some question whether it's true to the data or not, actually. But that's beside the point. It's true, it's more or less true to the data, except that it's highlighting something that it doesn't matter in an election, right? This thing highlights how many counties were won in that election, which has nothing to do with who wins an election, right? What matters for who wins an election actually is not even either of these. It's not the popular vote, it's not the percentage of eligible voters. It's not the number of counties that you win, right? It's how many states you win. So the popular vote within states. So while this chart might be true, it's a complete misrepresentation of the way the election happened. Okay, the end. So now comes the fun part. Get to lie with visualizations. Yes. Okay, so I dropped in the, before we started, I dropped into the Slack a link to a Drive, Google Drive folder, and it has the slides for the activity, but I also bring them up here to talk to them. You know what you're actually going to be doing here. Okay, so this is called white hat, black hat visualization. So this is just like white hat, black hat hackers, right? White hat hackers are people who are hacking for the good, and black hat hackers are ones who are hacking for the bad. Okay. This comes from like old movies where the good guy would always wear a white hat and the bad guy would always wear a black hat, so that you knew who was who. Okay, not that you know who is who in the hacking world. Okay, so we're all tempted to think that data and data visualizations are neutral, but they're not, right? They're biased. You should assume that they're biased. Okay, so we always generate them with some perspective. In your papers, you're trying to convince people that the discovery that you made is true and interesting. For some of these other charts, people are trying to convince things of other things, like how much they won an election by, or how much more educated they are. So one thing that we have to think about when we're making charts is, are we actually making charts that are responsive? Okay, and this gets even like more squishy when you're doing public outreach. You want to make sure that the data that you're presenting is really telling the story that's true to the data, not a story that's somehow made up, because you really don't want to mislead the public if you can avoid it. Okay, so there are going to be a couple parts to this. The first part is, in your group, you're going to go ahead and you're going to pick a data set to work with. These are 3 data sets. They're on the boundary of being sort of controversial hot issues. They're not super controversial, but they're issues that people care about, let's say. There are a DEA pain pill database, so people misuse drugs. So this is a database of pain pill use. This is a database that looks at greenhouse gas emissions, so it's a climate change related one. And then this one is about several indicators of gender equity since the 1960s. Okay, so another thing that's an important cultural issue. Okay, so you as your group are going to pick one of these 3 data sets to work with. And what you're going to do is, with any tool you want, you're going to create a white hat visualization. So you're going to create a visualization for good. You're going to say, here's the great work we've done in gender equity over the past 50 years. And you're going to make a super fantastic visualization out of it. Okay. That means that it should be clear and easy to interpret for everyone. Anything that you're doing to the data should be well documented within the visualization you're making, or the caption that you're adding to the visualization. And if there is any bias in what you're presenting, it should be somehow noted in the picture that you're generating. Okay, so that's kind of the second part, really the first part that requires any work. Then what you're going to do is you're going to take that and you're going to do evil with it. Okay? So what you're going to do is you're going to start with that visualization and you're going to create a black hat visualization. And that's going to be a visualization intended to mislead. So it's not going to be genuine to what's happening in the data. It's going to do things that are somehow inappropriate, but you also want to make it somehow not obvious that it's been manipulated. Okay? And this is the fun challenge. Okay? These are some ideas for how you can make it, how you can manipulate it. The fun challenge is, at the end, You get to pick whether you give me your white hat visualization or your black hat visualization. I don't know, the rest of the group doesn't know. And then we're going to show each of them and we all get to guess whether it's a white hat visualization or a black hat visualization. Okay, so it's entirely up to you which of the two you want to submit. I recommend some of you submit white hat ones because if they're all black hat, won't be that much fun. But some of you should submit white hat ones, some of you should submit black hat ones, and we're going to guess it. Yeah. Any questions about that?